Good evening, everybody. Can you guys hear me okay?
Yeah, I can hear you.
Okay, thank you. What we're going to do today is we're going to move to parallel circuits. The lab before this is series circuits, but it's very similar to the lab that we did last time when we did the summary of equipment. I did put the link up. I did not put the link up for the extra credit yet, but I did put the link up for the lab, and I believe it's due tomorrow, if I'm not mistaken. So make sure you look at that due date for the lab that we did last class. So that's very similar to experiment number 7, which would have been one of the labs we would have done. Since it's so close, I decided not to do that one, just move straight to the parallel lab. I did put on Blackboard the document for you to print out. Hopefully you had a chance to print it out. If you didn't, you may want to bring it up and minimize it so you can look at it, refer to it as we go through the lab. This lab deals with parallel circuits, and just briefly, just to kind of remind you, I'm going to turn off the projector. So if you guys want to talk, you're going to need to text me or message me because you won't be able to use your audio when I switch this over. So I want to just go through a little bit of theory. If something's not clear or you need to ask me a question, just send me a message and I'll look at it. So let me switch over now. I just want to do a brief discussion of this and then I'll come right back to where you guys can talk. So I think to do that, let's just do this. Okay, so you know that if I have resistors, and I'm not sure where the field of the camera is, so I'm just gonna stay right here. So I have these resistors. I'll just do 3 of them. So I have these 3 resistors, R1, R2, and R3. And to connect these in parallel, as you know, I just take a line and connect the tops of the resistors together, and I connect the bottoms of the resistor together. And so when I apply a voltage source to this, V volts, if I put my multimeter across the battery and then walk across the circuit this way, I see that the voltage of the source is across the whole circuit, so each resistor in a parallel circuit gets the same voltage. And we discussed that in class. However, the current, as you can tell from the circuit, the current will divide. So my total current is here. When the current reaches that first connection of R1, it's going to divide, and so I have a branch current. That's called a branch current. We name that branch current. If I just have one resistor in the branch, I'll just name the current after the resistor. So this is R1, the current in R1, I'll call I1. I got I2, and I got I3. So this is nothing new. We talked about this before. And the fact that if I add up those branch currents, they got to add up to the total current. So I1 plus I2 plus I3 for this circuit, it's got to equal the total current. This is called Kirchhoff's current law. Kirchhoff's current law. Now, if you have the lab handout and you look at it, he states that another way. If you have the handout, take a look at your handout. Look at page 82 of your handout. And on page 82 at the very top, look at figure 9, figure 9-2. He shows, don't let the box confuse you. What he has is he has a connection of 3 wires. So he has something like this. He has a connection of 3 wires. And he has these currents going into these wires. So maybe and I might not have it exactly like he has it, but maybe I have a current there, and let me see how he has it. He has a current there, and he has I2, like right there, and he shows I3 over here. And the reason he put the box around there is that connection, that node, he's showing that the current entering the node has got to equal the current leaving the node. So he states it another way. In the box above figure 9.2, here's how he states Kirchhoff's current law. He says the sum of the currents entering a circuit junction is equal to the sum of the currents leaving the circuit junction. Essentially, that's the same thing as what we have over there. The current entering a node has got to equal the current leaving a node. So it's just stated a different way. So there's nothing new there. Now, when we looked at parallel circuits, one of the things we did, we derived basically three formulas. One of the formulas we derived, I call it the reciprocal rule or the 1 over R rule. And so let's talk briefly about that. I won't derive it because you already know it. But for this circuit, if I want to find the total resistance, you know that the total resistance, we call that REQ. I think on the handout he calls it RT. Is going to equal for this circuit 1 over R1 plus 1 over R2 plus 1 over R3. So you've seen that formula before, the reciprocal formula. But then there's this thing called conductance. Conductance. And we actually talked about conductance. Conductance is the reciprocal of resistance. And so if I want to find the conductance of a circuit, what I can do, I use the symbol G for conductance. I use a G for conductance. So G is 1 over R. So whereas resistance refers to how hard is it for current to flow through a certain material, conductance asks the same question, but the opposite way. How easy is it for current to flow through a certain material? So anything with a high resistance has a low conductance, or anything with a high conductance has a low resistance. They're reciprocals of each other. And because of that, in some books, when you look at this formula right here, these are reciprocals. So really you're adding up the conductances. So another way to do this formula, and that's what he does on the handout there. I'm just going over because he does it on the handout. This right here, 1 over REQ, will be my total conductance. And then this conductance, we'll call that G1. And this conductance, we'll call that G2. And this conductance, we'll call that one G3. I can add up those conductances to get the total conductance. And so usually when they show this reciprocal formula, a lot of books will show that you're just adding up conductances. And in the very end, once you get the conductance, if G equals 1 over R, that means that R is going to equal 1 over G. And if that's a total, then that's a total. So you can find the conductances real quick, stick it in this equation, and get your total resistance for the parallel circuit. So this is kind of a review. We've done this when we talked about parallel circuits. The other thing I want you to remember is that when I have resistors in parallel, I want you to remember two things. The total resistance of a parallel circuit is always less than the smallest resistor in the parallel string. So let's say that I have a resistance here of 20K, I got 10K, and I got 5K. When I add up those resistors using this formula, the total resistance of the circuit has got to be less than 5K. In a parallel circuit, the total resistance is always less than the smallest branch resistance in the circuit. And since the 5K is the smallest, then my total resistance has to be smaller than 5K. So that's one thing. The other thing I want you to remember, and you'll actually see this in the lab, I want you to remember that if I keep on adding resistors to the circuit, the total resistance is going to go down. So every time I add a resistance, adding resistance, if you think about it, if I increase the resistance, I add resistors, my conductance is going to go down and vice versa. So by adding resistance, I keep adding resistance, I keep increasing my conductance, which means my resistance has to go down. I actually proved this when we mathematically proved it when we studied this back when we looked at parallel circuits. So I won't go through that again. I'm just mentioning that because you're going to actually do that in real time in the lab, and I'll discuss that in just a minute. There are two new things, though, in the lab I want to point out that we did not talk about when we talked about parallel circuits. So I'll point those out, and then we'll go through the lab, and then we'll go ahead and do the lab. The new thing is there's two formulas called the current divider rule. Current divider rule. So let me write that on the board. Current divider rule. So it's the current divider rule or current divider formula. And there's two of them. There's a general rule, and then there is a rule, kind of a special case for two resistors. So I'm looking at page 82 of the handout. I don't know if you have it out or not, but at the bottom of page 82, if you have the handout, you will see both current divider rules. The one at the top is the general rule. The one at the bottom are special case rules. The special case is when you have two resistors. So let me deal with the one on the top first. So it's written like this. It says that Ix equals RT over Rx times IT. So this is the general form of the current divider rule, and I want to go over this because this can be a little bit confusing if you just look at the formula. So first of all, look at page 84 of your lab. If you got the handout, turn to page 84 and look at page 84. If you look at page 84, table 9-4. In table 9-4, you see that you're actually going to use this formula, so I want to make sure you understand how to use it. Okay, so this is a general form of the current divider rule. You might remember that we studied the voltage divider rule in the class, and that's just a quick way of finding the voltage drop across the resistor. But the current divider rule is supposed to be a quick way of finding a branch current to the resistor. And so here's how it works. Let's say we didn't know these values. I'm just going to keep it general. But this is confusing because when you see RT, what I told you in class was if I'm finding the total resistance of a series circuit, I'm going to call that RT. If I'm finding the total resistance of a parallel circuit, I'm going to call that REQ. And the way I get REQ is by using the reciprocal rule to find REQ. Well, really, that RT, you probably want to just, on your lab, that's really REQ. Because to find that, you got to use the reciprocal rule. So to find REQ, I will go 1 over REQ, and then I'll put these values in over here. This will be 1 over R1, plus 1 over R2, plus 1 over R3. And once I found that, I will put that in this formula. So that's important that you understand how to do that because you'll have to do that for the lab. So this REQ, you don't add the resistors up. You actually use the reciprocal rule to get the numerator here. And then what it says is, let's say I want to know the current through this resistor. I'm going to call that Rx. If I want to know the current through that resistor Rx, remember we named the current after the resistor. So if I call that Rx, then I got to call this Ix. And all this says is, if I want to know the current through resistor Rx, I put that in the numerator. I divide that into the total resistance, REQ. So remember, I got to get that REQ by doing the reciprocal rule. I take that fraction and I multiply by the total current. So what you got to know to do this, you got to know this piece right here. You got to know the value of this resistor. You got to be able to calculate REQ, and you got to have the total current. And then you can use those values to find the current in the resistor, the resistor in question. You can use that. So that is a general form of the current divider rule. So make sure you follow that. If you don't follow it, you can either ask me later on, or you can look at YouTube and they'll probably take you through the calculation. But it's pretty simple to use. In addition to the general form of the current divider rule, there's also a special case, the special case of two resistors. So let me put those formulas on the board. And honestly, I don't really like, I don't say I don't like it. I don't use the current divider rule often. I just use Ohm's law, but some people like to use the current divider rule. If you have the handout, look at the bottom of page 82 and you will see two formulas. One formula, I'll just write them both on the board. One of them says I1 equals R2 over R1 plus R2 times IT. So this only works if you have two resistors. So let me change this circuit over here to one with two resistors. And the way this one works is like this. Say I have two resistors in parallel. I know the value of those resistors. I also know this current. I know my total current flowing into here. And I either want to know the current here in that resistor, or I want to know the current here. Well, this one right here is for I1. So here for this, you want to know the current right here. And the way it works, you just kind of got to follow the pattern. Notice I want to know the current in R1, but in the numerator I got the opposite resistor. And that's the way you do it. The denominator will stay the same. It's always R1 plus R2. But if I want to know the current in this resistor, then in the numerator over here I have the opposite resistor. If I want to know the current in this resistor, then in the numerator I would have R1. So you can see, if you look at the formula on the sheet, I want to know I1, I want to know the current in this resistor, so I'm going to have the opposite resistor in the numerator. So that's a special case of the current divider rule, two resistors. Now you're going to use the general form of the current divider rule when you do the lab. So if you have the handout, let's just kind of go through it real quick. This lab is pretty straightforward. So I'm going to give you a chance. Hopefully you had a chance to read it. I'm going to go through it, tell you how to solve it, give you a chance to build the circuit, and then I'll show you how I'll do my circuit build. So if you have the lab out, in these labs, make sure you do the summary of theory. So that's, if you read it, the very first thing is the objectives in the lab, and you want to read the objectives, because when you write your conclusions, you got to speak to the objectives, but I'll talk about that in a second. They gave you a list of materials. Now look at your list of materials, and go ahead, and I'm going to pause for a second, because I went through the parts I have, and they have resistors that you need, 4 resistors. You need a 3.3K, you need a 4.7K, and a 6.8K. And a 10K. So I went through my resistors and I was able to find everything except for the 6.8. So I'm going to pause for a second, and what I want you to do is get your resistors out and go through your resistors and ohm them out. You can either color code them, you know how to color code, or measure them and see which of those resistors you have. You should have a 3.3K, you should have a 4.7K, you should have a 10K. If you have a 6.8K, let me know. I could not find one in the parts that I have, but I did get something close. So go ahead and ohm those resistors out, and then what you want to do is just write it on a sheet of paper and put the resistor down below it. So label the resistor so you can find it quickly. So I'm gonna give you a second to ohm those resistors out, lay them out so you can get them, and I'll come back in just a second. All right. So when I went through my part list here, and I have the same packet of parts that you guys have. When I went through it, what I found was I had a 3.3K, I had a 4.7K, I had a 10K, but I did not have a 6.8K. So what I'm wondering about you guys, let me go ahead and turn my audio on here. Okay, so you guys should be able to talk now. Does anyone not have a 3.3K? Does everyone have a 3.3K?
The closest thing I could find to the 6.8 was a 6 ohm resistor, or 6K resistor, actually.
Yeah, that's what I found. So are you guys agreeing with that? That the closest thing that we had to, they may not have had any 6.8K, and so they may have put in this place a 6K. So let me ask this question. Does everyone have a 6K resistor? Does anyone not have a 6K? I had two of them in my kit.
I had a 6.75.
Oh, you do have a 6.75. Okay. So it looks like some of us have 6.8K and some of us have 6K. So is there anyone that doesn't have either a 6.8K or something close or a 6K or something close? Is there anyone that doesn't have either of those two resistors? Okay, well, I'm assuming you have either something close to 6.8 or something close to 6K. So what I want you to do on the handout, if you have a 6.8K or something close, you don't have to change anything. However, if you have a 6K or something close to that, then on the diagram right here, figure 9.4, you need to cross that value out and write 6.0K. And then in table 9-1, resistor R3 is 6.8, cross that out and write 6K. So it sounds like everyone has the lab parts. The only one that might not match exactly is a 6.8K resistor. We can work around that. That's not a big deal. So let me go through the lab real quick, and then I want you guys to build it. So again, on the front page of the lab, you have your objectives. Now the objectives are important because when you write your conclusion, you want to make sure that you talk about each of the objectives and what you did to meet the objectives if they were met. There's a list of materials. We already went over that. The summary of theory is for you. I'm not going to talk about it. I kind of did a little bit of a lecture on it, but I think this author for this lab book does a really good job of explaining things. And so we talked about parallel circuits, but here you get to hear it in a different voice. So I highly recommend reading the summary of theory for two reasons. Reason number one, you get to hear it in another voice. And reason number two, sometimes when you do, sometimes the evaluation and review questions, which is how you're going to be graded on this lab, sometimes the answers to those are in the summary of theory. So you want to make sure you read it so that you know the answers. So that's on page 81. Now on page 82, you have table 9-1. So in table 9-1, what you're going to do is you're going to take your resistors. You have these three, and then you have a 6.8 or a 6K, and you're going to measure those with your ohm meter. So you should fill that out. Once you've measured with your ohm meter, in table 9-2, what you're going to do is you've already measured the value of R1 in table 9-1 because you have it written there, right? You've already measured that value for R1. So whatever value you get for a measurement for R1, transfer that measurement down to table R2 or table 9-2 for R1. And then what they want you to do is if you look across that first row of table 9-2 where it says RT measured, they want you to hook up your multimeter to R1 and then add R2 to it and write down what the total resistance is, add R3 to it and then write down what the total resistance is, and then add R4 to it and write down what the total resistance is. So in effect, what you're going to do is start with one resistor. You're going to hook up your ohm meter. So you got your ohm meter here. Hook it up across R1, and you'll read the value of R1. So R1 is 3.3K. So this will read something close to 3.3K. And then while your meter's still connected up, what you're going to do is connect up another resistor, R2, across R1 like that. You'll connect up R2. And what you should see is the total resistance drop. You'll write that value down, R1 parallel R2. And then you'll add another resistor in parallel, R3. And you'll see the resistor drop even more. And then finally, you'll add that fourth resistor, R4. And then you'll have all resistors in parallel. And what they want you to see is they want you to prove to yourself that as I keep adding resistors in parallel, my total resistance is going down. That's what you should see. That's the effect you should see. And so that's the first part of table 9-2. Once you've done that, they want you to measure the current. So we haven't done any current measurements yet. So I'm gonna hold off on the current measurements until we get the circuit built. But basically in this lab, there's only 3 measurements you gotta make. You gotta do the measurements for resistor measurements, R1 by itself, then R1 parallel R2, then R2 parallel R3, then R1 parallel R2, parallel R3, parallel R4. That's the first row of table 9-2. That's one value. Then you gotta measure. And then you gotta measure, to finish out table 9-2, they want you to measure current. And then once you've done that, read procedure 5 at the bottom of page 83. Take a second and read that. If you read procedure 5, it says measure the voltage across each resistor. How does the voltage across each resistor compare to the source voltage? So what they want you to do is hook up the circuit now. You hook up your voltage source over here, and you're going to set it to 12 volts. You're going to take your voltmeter and go across each resistor and measure it, and they want to know how does that compare to your total voltage, your source voltage. Well, of course, you know in the parallel circuit, the voltage is the same everywhere. So what you should see happen is the voltage across each resistor should equal the source voltage. That's what you should see. But again, in lab, they want you to prove it to yourself. So that's what you write down there for procedure 5. So once you measure, once you fill out table 9-1, and then you fill out the first row of table 9-2. Then we measure the current, and then you do that measurement for procedure 5. Everything else in the lab is calculated. If you flip over to the next page, they're going to have you for table 9.3 and table 9.4. All you're doing is you're finding the branch current. You find the branch current in the circuit 2 different ways. One way using Ohm's law, table 9-3, and the second way using the current divider rule, table 9-4. There is one more thing that you have to do though. In table, if you look at procedure 9, everybody on page 84, procedure 9. Don't forget to do this. Don't disconnect your equipment until you do this. It says simulate a burned out resistor by removing R4 from the circuit. What's the new total current? So here's what I want you to do. I want you to go ahead and build the circuit. The circuit is on page 83. Before you build the circuit, do what they want you to do in table 9-2. Go ahead and fill out table 9-1 if you haven't already done it. Measure those resistors, and then move R1, value of R1 in the table 9-2, and then go ahead and get all those resistors in parallel and get the measured value for each resistor in parallel. So I'm going to give you a chance to do that. I want you to try to do it first, and I'm going to project it on the board, and I'll do it, and then kind of walk you through the lab. So go ahead, get your stuff out. Try to, what I want you to do, I'm going to pause. I want you to try to do procedure, look at the procedures. Because right now, procedure number 1, procedure number 2, procedure number 3, and stop there. So procedure number 1, 2, and 3. I'm going to pause and give you a chance to do it, and I'll hook up my board and we'll do it together. So I want you to do, in the next few minutes, procedure number 1, procedure number 2, procedure number 3, and then we'll pause, and then we'll do it together. So go ahead and do that, and I'll leave this open so you can talk to me, but then when I want to do my lab, I'm going to have to turn it off and project it up on the board. So go ahead and do it. In case you have any issues or problems, I'll be right here. Do procedure 1, procedure 2, and procedure 3. All right. So guys, what you got to be able to do first is, this is the board from last time. So I don't know if you still have your power hooked up to these rails. Let me turn the light out and see if this is better. I don't know if it's better with the light out. I don't know if it really makes a difference. Okay, so I'm going to take R1. So I'm not going to worry about power yet. As a matter of fact, I'm going to disconnect this for now, just to get it out the way. Because I'm doing the first part of the lab, where they want you to, so I'm assuming already you've done number one. Number one says, obtain the resistors in table 9.1, measure and record the value of each resistor. So I've done that already. Procedure 2. In table 9.2, you will tabulate the total resistance as resistors are added in parallel. Parallel connections are indicated by two parallel lines shown between the resistors. Enter the measured value of R1 in the table. That's the first thing you do. So R1, what is R1? R1 is the 3.3K. So I'm going to get my 3.3K, and I'm going to add it. Now I want to be able to hook these up in parallel. So here's what I can do. Remember this line right here? This line right here, that's a rail. This line right here goes all the way down the board. And there's a separate line above it that goes all the way down the board. So what I can do to hook these up in parallel, let's say I got two resistors I want to hook up in parallel. Let's say I got this one. So I got that resistor. And I want to hook another resistor in parallel with it. So let me grab another one. So I got that one. Let's say I want to hook it in parallel with this second resistor. What I can do is get two jumper wires. Because for resistors in parallel, you got to connect the top parts together and the bottom parts together. Now you could just move this over here like this, but you don't want to do that. You want the circuits to stay neat and clean and easy to troubleshoot. So what I got to do is take a wire from this column to this column to connect the tops together, and then from this column to this column to connect the bottoms together. So one way of doing that is I can get a wire. I got this wire, and I can connect one to R1 and the other one to R2, like that. And then I can take my second wire and connect to the bottom of R1 and then to R2, like that. You can do that if you want to. But then for every resistor, you got to have two sets of jumper wires. So what I want to show you is, since this rail right here is a wire that runs all the way across, we can cheat, and we can, for this green wire right here, we can just use the rail. We can use that rail as a wire, and we can have, the only thing we got to jumper is the bottoms. So what I'm saying is, I can take this off, and my R2 is 4.7K, so let me actually get 4.7K. So here's my value of R2. And what you can do is just move this up to the rail, like that. They want you to have your meter hooked up to this. So you're measuring the value of R1. So I can take my meter and connect that across R1. So R1 is supposed to be 3.3K, and right now my meter is reading 3.29. So while that's hooked up, they hook up R2. So I can use this rail right here as a wire. So let me take this off so you can see it. I can use this as a wire. I can just stick this in that top rail. And now that resistor is connected to this resistor through the rail. I never have to use that jumper wire. So I do have to use a jumper wire on the bottom, or if your resistor is long enough, you can bring it all the way down here to that bottom rail. If you don't want to do that, let me see if my resistance is long enough. It might be long enough to bring it all the way down here to that bottom rail. See, this one will reach. So this will reach in the bottom rail. And then, now watch what happens when I hook this other resistor up. So here is R1 by itself. Remember, that was like 3.3K. I'm going to take this other resistor and connect it to that bottom rail, and then it'll be in parallel with that first resistor. And I should see the reading here drop. So I'm going to go ahead and make that connection. And you see it drop to 1.94. So that's what you want to do. Just keep, now notice I'm not using any jumper wires here because I was able to stretch my resistors between these two rails. And if you remember from that handout before, these rails are like wires that run all the way down the board. So you can quickly add your resistors in parallel. So you go ahead and do that. I'm going to finish hooking this up. But you need to add R3 and get the measurement in parallel, R4 and get the measurement in parallel. Do that for all the resistors. So I need my 6.8, but I don't have a 6.8. But I do have a 6. So I'm going to use a 6. And then the last one is a 10. So I'm going to use a 10. I'm having a little trouble because my leads on my 10K are kind of short. I'm going to see if I can make it work. All right, so I got all my resistors in there, and my total resistance is 1.2K. 1.2K. Now, I'm using a 6K instead of a 6.8K. So if you're using a 6.8K, your total resistance might be a little different. So go ahead and do that. Get all your resistors hooked up, and at that point, you should have the first part of the first row of table 9-2 filled out. So you see how I have that hooked up? If your resistors won't reach from one rail to the next, just hook up the top rail and then just daisy chain them together at the bottom using the wire for the bottom part of it. Okay, now does anybody have any questions before we go to the next part? Is everybody getting the values they should get? You'll have to send me a text. And the people calling in by phone, I guess you can text me. I don't know if you can text or not. I don't know how that works. Okay, so I'll give you one more minute to get all your parallel resistor values measured, and then we're gonna move on to the next part, which is procedure 4. So I'll give you about another minute, and then we'll move to procedure 4. Okay, so procedure 4, let me read it. Procedure 4, complete the parallel circuit by adding the voltage source and the ammeter shown in figure 9.4. Be certain that the ammeter is connected in series with the voltage source as shown. If you're not sure, have your instructor check your circuit. Measure the total current in the circuit and record the value in table 9.2. So here's what I want you to do. Measuring current can be tricky. If you get it wrong, then you'll end up blowing the fuse in your meter. So what I want you to do is hook up figure 9.4. Do not hook the ammeter up. Just hook up the power to your parallel resistors. See if you can figure out how to do it. You need to adjust your voltage to 12 volts. On the schematic, they have a source voltage of 12 volts. Do not put the ammeter in there. We'll do that together. I'll show you how to do it. So I'm going to give you a second. The object is that you learn, I mean, you can follow me all night long and do it, but you need to know how to do it yourself. So I want you to try to do it before I show you, and that way if you get something wrong, you can see what you did wrong, and eventually you'll get it. So the job is you got these resistors in parallel. I want you to adjust your source voltage to 12 volts, and then connect the 12 volts to these parallel resistors. See if you can figure out how to do that. Give you a few minutes to do that. All right, so I want to connect my power to my circuit over here. So just so you can see, I'm going to remove these leads. Now you remember from our first lab the other day that when you use power, you're going to use ground. This is the ground output. And then you have a plus V and a minus V variable output. We're going to use the plus V. We always use the plus V. So I already have a wire down here. You might have that from the previous lab. But you need to hook a wire to your ground output, and you need to stick a wire in your positive out V variable output up here. So I got the wire here. That's my positive voltage. I'm going to just stick it over here in this rail. So since it's stuck in that rail, I now have voltage to this resistor, but since that rail is all the way down here, it's a common rail, all these resistors now is connected to my positive V. I'm going to do the same thing down here for my ground, or my negative V. I'm going to connect that down to that bottom rail like this. And so now my negative voltage is here, my positive voltage is here, my power supply VS is now connected to my circuit. Once you connect it to your circuit, what you got to do is you have to adjust your voltage. They want 12 volts. So I'm going to take my my digital multimeter, and I'm going to change it to the voltage setting, which is on this side. And since I know I need 12, I'm just going to move it over here to 12. So I'll take my meter and I'm gonna hook my meter right across that first resistor. You might ask yourself, well, why are you hooking it across the first resistor? I need to hook it to the power supply. Well, remember the power supply is in parallel with these resistors, and all resistors get the same voltage. So if I measure any voltage across any resistor, I'm measuring the voltage of the power supply. So I have it hooked up to the circuit. I'm going to turn it on, and I'm going to adjust my voltage to 12 volts. I think I got a bad lead here. All right, my voltage is jumping around. I don't know if you can see my meter or not. I'm trying to get it in. Let me move these over so you can see this better. I'll give myself more room. All right, so there's my voltage. I got 10.5 volts. So what I'm going to do is this knob over here, this one over here, I don't know if you can see it in the camera. At the lower, let me move the camera over. So if you can see down here, this knob down here is what I want to adjust the positive voltage. So I'm going to adjust this up so that my power supply reads 12 volts. So let me make the adjustment. All right, so I'm pretty close to 12 volts. Okay, so is everybody with me here? I've hooked up my power supply to the resistors. I got my meter across the first resistor, so it's actually measuring the supply voltage, and I've adjusted my supply voltage to 12 volts. So now I know it's 12 volts. Now what you got to do now is you got to measure current, and we've never measured current before, so I need to show you how to do that. So let me mute this and go to the board. Measuring current can be a problem if you don't know what to do. Voltage is across a device, current is through a device. So let's say I want to measure, let's say I have a simple circuit. So I got a battery and a resistor. I want to measure the resistance across the resistor. I want to measure the voltage across the resistor. I want to measure the current through the resistor. So I take my digital multimeter. If I want to measure the resistance, the first thing to remember is you cannot measure the resistance while it's hooked up to the power source. You can't do that. So if I want to measure resistance, the first thing I would do is disconnect it from the power source. I take my digital multimeter hooked up as an ohm meter, and I put it across the resistor like that, and that will give me my resistor value in so many ohms. So I can measure this. I then want to measure the voltage. So to measure the voltage, I go ahead and connect the resistor back up to the circuit. I change my setting from ohms to volts. So now I'm on my multimeter, I'm reading volts. And I still leave the leads across the resistor. And I'll measure the voltage across the resistor. I'll get so many volts. So I'll measure that. So notice for both resistance measurement and for voltage measurement, my leads are across the resistor. Those are the only two measurements where your leads are across the resistor. Anytime you want to measure current, you can't have it across the resistor like that. What you got to do is you have to open up the circuit and actually physically put the meter in series with the thing you want to measure. So what I'm saying is, if I want to measure current to the resistor, I don't put this on amps and then put it across the resistor. You mess the meter up if you do that. What you do is you take your ammeter, you open up the circuit. So I open the circuit here, and you're going to use the meter leads to complete that bridge, that gap right there. So I'm going to put one lead here and one lead here. I use the meter leads to bridge that gap, that open circuit I made. So now current has to do this. Current has to actually leave the source, go through the meter, then get to the resistor. Current has to flow through the meter for it to read current. So you never put an ammeter across a circuit. You got to put it in series with the thing you want to measure. What do we want to measure here? Well, we want to measure the current, but we want to do it twice. We want to do it for, right now we're on what? Procedure, we're on procedure 5. No, we're on procedure 4. It says complete the circuit by measuring, complete the parallel circuit by adding the voltage source and the ammeter. So we're going to add ammeter to that. Well, before we get to that, what I would do, guys, is just go ahead and let's get number 5 out the way. Since we already got it hooked up, let's get number 5 out the way. For number 5, they want you to measure the voltage across each resistor to prove that it stays at 12 volts. So I'm not going to do it. You go ahead and do it. Just take your leads and move it across all resistors, you know, here and here and here to make sure that the voltage is the same. And then go ahead and fill out procedure 5 and you'll be done with that. So go ahead and do that. And then I want to show you how to hook up the ammeter. All right, now, so to hook up the ammeter, what you got to do is first set your meter up as an ammeter. Now, I'm not looking at your meter, so I don't know how yours is set up. But on this one, what you're going to do, on this meter, remember I said that you always use common? So this common wire down here is always used. So on your meter, I know the black goes in the common. Now the red, you got to look at the amp measurement. So on this meter, I see that this is the 10 amp input, and then over here I have the milliamp input. I don't know if you can see it right there, but that's the milliamp input. Yours may have a separate milliamp input. Sometimes it's the same as the volts, ohms, and amps all in one, and sometimes you have volts, ohms as one, and then current as another. You got to figure that out. But whatever you have, you got to have the black lead in common and the red lead in either milliamps. You don't want to put it over here in amps. Find your milliamp input. So your black lead is in common, and one of the inputs on your meter will say milliamps or microamps. Plug that one into there. And now you have it set up as an ammeter. Now, to actually hook it up to your circuit, what you got to do is open up the circuit. So how do you open the circuit? You just take the power wire here and you pull it out. So I got that power wire out. Now this is the gap I'm talking about right here. The power wire was hooked up to that rail. there's an open circuit between here and that first resistor. So I'm going to use my meter leads to complete that gap. So I'm going to take my red lead and put right here. I'm going to take my black lead and complete the gap. There, I'm going to fill the gap in like right here. And I'm going to put my meter on amps. And I don't know if you can see what I'm reading, but I'm reading 9.2 milliamps. 9.2 milliamps. Well, I don't know if that's correct or not. So how would you know if it's correct? Well, you can check to see if your answer makes sense by just doing a little bit of math. You know your total resistance. I forgot what my total resistance was. I think it was I forgot what it was, but you know your total resistance from your table. And we know we got 12 volts. So if you take 12 volts divided by whatever that last column is in table 9.2, where you have resistor R1, R2, R3, R4, you should divide 12 volts by your total measured resistor value, and you should get something close to what your meter's reading. So I'm reading 9.2 milliamps. You should get something very close to 9 milliamps. And I think if you do the math, you'll see it's very close to 9 milliamps. So I'm pretty sure mine is correct. Now, does anybody have any questions? You see what we're doing? You have to text me if you do, because I don't. Okay, so the only other part of the lab you need me for, once you get that current measurement, then look at your lab. Now, don't forget to do number 5. You measured across each resistor. But go to page 84 of the lab and read procedure 9. Read that to yourself. Procedure 9 says, simulate a burned out resistor by removing R4 from the circuit. What is the new total current? So you're going to actually remove, while you have the meter hooked up, you'll remove R4 from the circuit. Now, before you do it, think about what's going to happen. If I keep adding resistors in the parallel circuit, the total resistance goes down, which means the current goes up. So if I remove a resistor, instead of adding a resistor, I would expect the current to drop down. And so let's do that. I'm gonna remove the resistor, and let's see what happens to the current. I'm gonna remove R4. So right now I'm at 9.2 milliamps. If I pull this resistor out, it drops to 8 milliamps, as expected. So I'm going to give you kind of just a piece of advice, because when you do your evaluation and review questions, what you got to do on here to get credit, turn to page 84 and read your evaluation and review questions for me. Just page number 1. Read number 1. It says in step 9, you simulated an open resistor by removing it from the circuit, and you observed that the total current dropped. Explain how the open circuit could be found in this experiment from the observed change in current and source voltage. Now, I want you to be clear on what they're asking. Let me ask the question another way. You know we got 4 resistors, and you know the value of those 4 resistors. You also know the total current because you just measured the total current. My total current was 9.2 milliamps. When I remove R4, the current dropped from 9.2 milliamps to 8 milliamps. It dropped by 1.2 milliamps. Is there a way of just looking at the change in current, where we started and where it ends when I remove a resistor, is there a way by looking at that change in current to determine which resistor I removed? I know I removed R4 because they told me to, but let's say I put R4 back and all you could look at was the meter, and I took and removed another resistor, the current's going to drop to a different value. Is there a way to figure out which resistor I removed by looking at how much the current changed? And so you want to use that and figure out evaluation and review question number 1. Most students get that question wrong. So hopefully you understand the question and you can answer it correctly. Now I'm about to turn this off so I can see if you guys have any questions. So hopefully you got your circuit hooked up and everything worked out okay. I'm going to turn this off. Okay, now you guys should be able to hear me and I can hear you. Does anybody have any questions, issues, or problems? Okay, well, I will assume your lab you were successful with this experiment. If not, you know how to go to Blackboard and you can watch it and just kind of go through it. I think your experiment from yesterday is due, I want to say tomorrow, but check on Blackboard. But go ahead and get that one out the way, and that way you can spend some time answering the questions here. You can finish the rest of the lab yourself. I think if you read it, all you're really doing is using Ohm's law to fill out table 9.3, and then the new voltage divider or current divider rule to do table 9.4, and you're going to compare table 9.3 to table 9.4. So that's it for this lab. If you don't have any questions or comments, I will post another lab. This will be due soon. It will be due before Tuesday, and I'll post the next lab by Tuesday, and then you guys can we'll work on that one. So guys, have a great rest of the day. I will talk to you soon. Have a great weekend.
I have a question real quick. Sorry.
Okay.
On the lab from last night, did you want us to scan like the circuit we drew, or can I just snap a picture and throw that into my summary report on Word?
Yeah, just take a picture with your cell phone and just copy paste it into Word if you can. You don't have to scan it. Just include it in the Word and you'll be all right.
All right, cool. Thank you.
Okay, guys. See you later.